When we ask if there is a creator, the real question is, where did everything come from? If matter can't appear out of nothing, then what existed before the universe? Today, let's dive into one of the biggest mysteries of existence. The law of conservation of matter tells us that matter doesn't just pop into existence or vanish into thin air. It simply changes form, like water freezing into ice or evaporating into steam. But that raises a puzzling question. If all matter is just transformations of existing material, then where did the first bit of matter come from? It's like a video game. Where did the first gold coins even come from? Before answering that, let's tackle a few mind-bending questions. First, can matter and energy actually appear out of nowhere? Is the universe playing by the same rules as Harry Potter's magic tricks? Second, what happened in those first insane moments after the universe was born? Third, consider this. Our universe contains about 10 to the 55th kilograms of matter. That's a 1 followed by 55 zeros. Was all this matter here from the very beginning, or did it emerge in stages? If it came in parts, where did those later additions come from? And finally, where did that very first spark of matter originate? To even start answering these questions, we need to go back in time and see how the law of conservation of matter was first discovered. In 1756, Russian scientist Mikhail Lomonosov heated tin in a sealed container. The tin turned into white tin oxide, but when he weighed everything before and after, the total mass stayed the same. No matter what he tried, the numbers never changed. He called this the law of indestructibility of matter. 2 decades later, French chemist Antoine Lavoisier confirmed the same principle using ultra-precise measurements, proving that the rule applies even to chemical reactions. Fast forward to the 20th century, scientists conducted high-precision experiments and found that mass changes in reactions were so tiny they could be ignored. This law became an unshakable foundation of modern physics. But if matter is always conserved, how did it appear in the first place? To get closer to an answer, we need to rethink everything we assume about nothing. Because, as it turns out, empty space is never truly empty. The universe follows strict rules, and one of the most fundamental is the law of conservation of matter. This principle states that matter cannot be created or destroyed, only transformed. No matter what process occurs, from chemical reactions to nuclear explosions, the total mass remains the same. Even when a substance burned and seemed to disappear, its mass was still present in the form of gases. This discovery laid the foundation for modern chemistry. But what about extreme conditions, like the early universe? By the 20th century, high-precision experiments confirmed that, even in nuclear reactions, mass is conserved. Although Einstein's famous equation, E equals mc squared, showed that mass and energy are interchangeable. In practical terms, matter can transform into energy, and energy can form matter, but the total amount of substance in the universe remains constant. So if matter cannot appear out of nowhere, where did the first particles come from? The answer may lie not in matter itself, but in the very fabric of space and energy that existed before anything else. To uncover this, we must turn to quantum physics and the strange world of invisible fields. Most people think of empty space as truly empty, but in reality, the vacuum of space is anything but nothing. In quantum physics, empty space is a seething arena of activity, filled with fluctuating energy and virtual particles that pop in and out of existence. This strange phenomenon suggests that matter can appear, at least temporarily, seemingly out of nowhere. Quantum field theory, the backbone of modern physics, describes the universe as a vast network of invisible fields. Each type of particle has a corresponding field, and particles emerge when these fields gain enough energy. Think of it like climbing stairs. Energy levels increase in discrete steps, and when a threshold is reached, a new particle can be born. This brings us to the concept of vacuum fluctuations. Even in what we call a vacuum, quantum uncertainty causes tiny bursts of energy to appear and vanish in an instant. These fluctuations give rise to virtual particle pairs, matter and antimatter appearing together before annihilating each other almost immediately. While this doesn't mean stable matter is spontaneously forming everywhere, it does suggest that the universe is not bound by the classical idea that something cannot come from nothing. But if these fleeting particles exist everywhere in space, could something similar have happened at the birth of the universe? To answer that, we need to dive into the world of Heisenberg's uncertainty principle and the hidden energy of the vacuum itself. Quantum field theory is the invisible framework that governs everything in the universe. It merges quantum mechanics, special relativity, and classical field theory into a single system that describes how particles interact. According to quantum field theory, particles are not standalone objects, but excitations of fundamental fields that extend throughout space. Imagine these fields as an ocean, normally calm and uniform, but when energy disturbs it, ripples form. These ripples are what we perceive as particles. Every known force and particle, from electrons to photons, arises from a corresponding field. For example, the electromagnetic field gives rise to photons, while the Higgs field gives particles their mass. One of the most astonishing implications of quantum field theory is that even a vacuum, seemingly empty space, is filled with fluctuating energy. Physicist John Wheeler estimated that the energy density of a vacuum could be as high as 10 to the 13th joules per cubic millimeter. This vacuum energy allows virtual particles to emerge briefly, hinting at the possibility that the very fabric of space-time contains the ingredients needed to create matter. If particles are just excitations of fields, then where did the first excitations come from? If a vacuum can hold such immense energy, could it have played a role in the birth of the universe? To explore this, we turn to the Heisenberg uncertainty principle and the unpredictable nature of quantum fluctuations. Quantum fluctuations are tiny, spontaneous bursts of energy that constantly occur even in empty space. According to Heisenberg's uncertainty principle, the more precisely we measure one property of a particle, the less precisely we can know another. This means that energy can momentarily appear out of nowhere, as long as it disappears quickly enough to avoid violating conservation laws. In 1927, Werner Heisenberg formulated this principle, which revealed that quantum particles don't have fixed states until they are observed. This was later confirmed through experiments like Thomas Young's famous double-slit experiment, where photons behaved as both waves and particles depending on whether they were measured. One of the most bizarre consequences of quantum fluctuations is the existence of virtual particle pairs. These particles and antiparticles spontaneously emerge, exist for an instant, and then annihilate each other, releasing energy. This process happens everywhere, all the time, and has even been observed near black holes, where it contributes to Hawking radiation. If the vacuum is constantly bubbling with energy and fleeting particles, could something similar have happened on a much larger scale at the birth of the universe? To find out, we need to explore how fundamental symmetries in physics connect to the conservation of energy itself. In 1915, mathematician Emmy Noether uncovered a profound link between symmetry and conservation laws, now known as Noether's theorem. It states that every fundamental symmetry in physics corresponds to a conserved quantity. For example, the fact that the laws of physics remain unchanged over time leads directly to the conservation of energy. In simple terms, if the rules of the universe don't change from one moment to the next, energy must remain constant. Similarly, the uniformity of space ensures the conservation of momentum, while rotational symmetry guarantees angular momentum conservation. These ideas reshaped modern physics, influencing everything from quantum mechanics to general relativity. However, the early universe was anything but stable. Space-time itself was expanding and transforming at an extreme rate, meaning that some conservation laws, including energy, might not have applied in the same way. In fact, in general relativity, energy conservation is not as strict as in classical physics because space-time itself can gain or lose energy. This raises a fascinating question. If energy wasn't perfectly conserved during the Big Bang, could that have allowed the creation of matter? Around 13.8 billion years ago, all the matter and energy in the universe were compressed into an unimaginably tiny, dense singularity. Then, in an instant, the Big Bang occurred, an event that marked the rapid expansion of space itself, not an explosion in the traditional sense. In 1929, astronomer Edwin Hubble provided key evidence for this theory by observing that galaxies were moving away from us, with more distant ones receding faster. This cosmic expansion suggested that, if we rewound time, everything must have once been packed together in an incredibly hot and dense state. In the 1940s, physicist George Gamow expanded on this idea, proposing that the early universe was a high-energy plasma, with particles constantly colliding. As it expanded and cooled, protons and neutrons combined to form the first atomic nuclei in a process known as nucleosynthesis. In 1964, Arno Penzias and Robert Wilson accidentally discovered a faint background radiation coming from every direction in the sky. At first, they thought it was interference, possibly from pigeon droppings on their equipment. But after ruling out all possible sources, they realized they had stumbled upon something extraordinary: the cosmic microwave background, CMB, the afterglow of the Big Bang. This radiation, with a temperature of just 2.7 Kelvin, is the cooled remnant of the intense heat that filled the early universe. Predicted by physicist George Gamow and his colleagues in the 1940s, the CMB provided the strongest confirmation yet that the universe began as a hot, dense state before expanding and cooling over billions of years. Satellite missions like KOHB, WMAP, and Planck later mapped the tiny fluctuations in the CMB, revealing the seeds of the large-scale structures we see today: galaxies, clusters, and cosmic filaments. These slight variations in temperature hold clues about the conditions of the early universe, helping scientists refine our understanding of its origins. But while the CMB confirms the Big Bang, it also raises new questions. What caused these fluctuations? And what force drove the universe's expansion in its earliest moments? The answers may lie in an even more mysterious phenomenon: cosmic inflation. As you know, Hubble discovered that galaxies are moving away from us. This cosmic redshift, where light from distant galaxies shifts toward the red end of the spectrum, was clear evidence that the universe is expanding. Imagine the universe as a giant balloon, with galaxies as dots on its surface. As the balloon inflates, the dots move apart, not because they are traveling through space, but because space itself is stretching. Decades later, more precise measurements confirmed that this expansion wasn't slowing down, it was accelerating, driven by a mysterious force known as dark energy. Dark energy is thought to make up about 70% of the universe, yet its nature is unknown. One possible explanation comes from Einstein's cosmological constant, a term he originally introduced and later dismissed as a repulsive force balancing gravity. Now, it seems Einstein may have been right all along, as dark energy behaves like an intrinsic property of space itself. Another theory suggests that dark energy comes from quantum fluctuations in empty space, a consequence of vacuum energy. However, theoretical calculations predict an energy density far greater than what we observe, making this an unresolved puzzle in physics. As the universe continues expanding, dark energy may shape its ultimate fate. If dark energy remains constant, the universe will continue expanding indefinitely, growing colder and more desolate over time, a scenario known as the Big Freeze. However, if dark energy strengthens, it could eventually overcome all forces holding matter together, leading to the Big Rip. In this case, galaxies would be torn apart, then stars, planets, and even atoms themselves would be shredded as space stretches uncontrollably. Some calculations suggest this could happen in about 20 billion years, but the exact timeline remains uncertain. Alternatively, some theories propose a big crunch, where expansion reverses, causing the universe to collapse back into a singularity. Others suggest a big bounce, where a new universe could emerge from the ashes of the old one. For now, dark energy remains the deciding factor in this cosmic story. If matter cannot be created from nothing, then where did the first particles in the universe come from? The answer may lie in the physics of the early universe and the strange properties of quantum fields. During cosmic inflation, the universe expanded exponentially in a fraction of a second. The energy driving this expansion was eventually transferred into ordinary matter through a process called reheating. As space cooled, energy from the inflaton field decayed into fundamental particles, including quarks, electrons, and photons. Quarks combined to form protons and neutrons, And after hundreds of thousands of years, these particles came together to form the first atoms. Before the Big Bang, the total amount of matter in the universe may have been minuscule, perhaps equivalent to just a few hundred carbon atoms. Yet, through rapid expansion and energy transfer, this tiny seed of matter was amplified into the vast cosmos we see today. Some scientists suggest that the initial matter came from interactions between quantum fields, while others propose that matter-antimatter asymmetry played a key role. But one question remains. If the universe needed an initial seed of matter, where did that seed come from? One idea is the cyclic universe model, proposed by Roger Penrose's conformal cyclic cosmology. It suggests that our universe is just one in a series of endless cycles, where the far future of one universe becomes the Big Bang of the next. In this view, matter doesn't appear from nowhere. It transforms across different cosmic eras. Another possibility is the quantum bounce model, which suggests that the universe never truly reached a singularity. Instead, quantum gravity effects caused a previous collapsing universe to rebound, creating a new expanding universe. This theory avoids the problem of matter appearing from nothing by suggesting that a universe always existed in some form. Other models, like the multiverse theory, propose that our universe emerged from a larger cosmic structure where new universes constantly form. If true, our Big Bang might have been just one event in an endless cosmic landscape. Though these ideas remain speculative, they offer intriguing possibilities about what came before everything we know. The answer, if we ever find it, may completely reshape our understanding of reality itself. Despite all we've learned, many mysteries remain. We know matter can't appear from nothing, yet the universe is full of it. Quantum fluctuations and cosmic inflation offer clues, but they don't fully explain the first spark. Theories like the multiverse and cyclic cosmology suggest possible origins, but without evidence, they remain speculation. Dark energy, the driving force behind expansion, is still a puzzle. Science has uncovered much, but the ultimate question, what started it all, remains unanswered. Perhaps future discoveries will finally reveal the truth about our cosmic beginnings.